What is up, you guys? I'm Charmx. Today I'm going to be reacting to Game Theory Mario's Lunar Apocalypse Super Mario Odyssey by the Game Theorist. Now, I don't know what to expect. Hopefully it's going to be quite interesting. Also, please forgive me if I'm not that crazy energetic or stuff like that. I feel sick at the moment. Something's wrong with my stomach. I don't know what it is. But yeah, anyway, with that being said, the original link's in the description. And let's begin.
Mr. MadPat, how many moons does it take to get to New Dog City?
Let's find out.
Why do you draw yourself with, like, the smallest body ever and the biggest head ever?
A 1, a 2, a 3.
20 minutes later.
46, 47, 48, 48 sugary moons. Now, if you'll excuse me, I don't feel too well.
Ba 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 da ba.
Welcome to Game Theory, the
I freaking love that intro. I love
funky
it.
mode to all of gaming's most complicated issues. Today we're gonna be strapping in and launching ourselves into Super Mario Odyssey, one of the most satisfying and confusing Mario worlds I've ever had to experience. I mean, you have a kingdom of rainbow forks right next to Nintendo's version of Dark Souls. Then, because of Mario's canon height of 5'1", the people of New Dong...
Is that how tall he is? I did not know that. 5'1". Mario is not also a plumber. He is a little person, apparently. Well, I guess that explains how he can run through sewers.
City are well over 10 feet tall, but of course Wario isn't in the game, so I can't prove once and for all that my calculations from 4 years ago weren't as insane as they initially sounded, okay? But you know, arguably the most fascinating part of this game has to do with the very last location you go to. The moon. Not because of the dark side stages or the boss rush, but because when you actually sit down and do the math, the moon is proven to be the single biggest threat to Mario. Nay, I say the entire Mushroom Kingdom. Forget Bowser and his petty little schemes to marry Princess Peach, that is nothing. This thing right here is a threat scarier than anything Nintendo has ever cooked up. We're talking Majora's Mask levels of planet-wide moon-based catastrophe here, people. But to truly understand why this thing, the moon, is such a menace to Mario in this game,
You better have a lot of proof to back up this claim, because for the most part, it's not like the moon's going anywhere.
we're gonna have to do some math. So get ready, theorists. Let's crack open some formulas and break out the TI-84s. Yeah, 84s.
Yeah, math. Woo!
We gotta bust out the big guns today, because here we go, off the rails to explore the great wide wacky world of Mario astrophysics. To begin, we need to first establish how large Mario's Earth and Moon are and how far these celestial bodies are away from each other. Now, by this point, you guys know how many headaches the Mario franchise causes me on the pixel measurement side. From shifting heights to wacky gravity, Mario isn't fighting Bowser so much as he's constantly fighting against my math. But determining the size of his planet in this game, this was the straw that broke the camel's back. I thought for sure that there would be a way to do it between...
Couldn't you just, you know, use our calculations, like what the real Earth is compared to the moon? 'Cause I'm pretty sure it's based off of that.
All the maps and globes that are present in the game's marketing and in the game itself. And let me tell you, I tried. I tried measuring pixels, but we had no consistently sized reference points. I tried measuring steps, but none of the stages allow you to truly see a whole continent. We attempted Al-Biruni's method, the Iranian scholar who determined the radius of the Earth by observing the heights of mountains, but without being able to reach a point on the horizon, we actually couldn't establish a distance between anything. I examined the globes, the brochures, the start screen, the opening menu, promotional materials for this damn game. So many different things. But damn it, Nintendo, you always have to make it difficult. So you know what? I gave up. You heard that right. I threw in the towel. To my
Quitter!
I'm a quitter!
Then again, I can't be too mad at him because I'm a quitter too. I quit. I've quit probably a lot more than Pat has.
My knowledge, there is no definitive way in this game to prove the actual size of Mario's planet and his moon. And I invite you all to try. Consider this the Mario Odyssey challenge. If you figure it out, we can do an episode dedicated to you and your math. And no, let me just nip this one in the bud right now. You can't assume that the hat ship on the overworld map is actual size. That would make the proportions of this globe absolutely absurd and wouldn't actually match up with what we see in game, where the actual hat ship or Bowser ship are much smaller relative to the actual size of the continent. Just throwing that one out there. Seriously, I feel like I tried everything here. However, just because I gave up on the measurement doesn't mean that the theory itself was in the pooper. Doing this for as long as I have, I know that there's more than one way to skin a Mario.
Oh, that's creepy.
Boy, that's a gruesome image. Sorry, that didn't come out right at all. Anyway, the key to this theory is the Roche limit, a theory concept first proposed by game theorist Reddit user Johnson and John Cena. For those of you who don't know, there's a magical distance a moon has to be away from a planet to remain a moon. Now, what do I mean by that? Well, think about it this way.
If it gets too close, it would get into the Earth's atmosphere and collapse into the Earth.
Planet or moon is held together by its own gravity, right? That's why all of these things are balls. All the stuff in the planet is being pulled towards the center, making it an orb in space. But remember, everything has gravity. Big things like the Earth, smaller things like the moon, even really small stuff like you or me, we all have those gravitational forces that act on each other. For instance, the Earth, under the influence of the moon's gravity, has whole continents raised about 50 centimeters because of the moon's pull on Earth. And
Really? I didn't know that.
conversely, the moon's surface shifts by about 5 meters towards the Earth in response to Earth's gravitational pull. And to make those facts even more incredible, remember, right now the moon orbits the Earth at an average distance of about 384,000 kilometers, or 238,000 miles. That is how strong the force of gravity is. So that begs the question, what happens when you bring those two objects closer together, where the big object, like the Earth, with lots of gravity, is able to pull even harder on the small object with less gravity like the moon? Well, something unexpected actually. The moon would get ripped to pieces because the Earth's gravity is stronger than the gravitational forces that are holding the moon together. You ever wonder
Oh, I get it. I get it.
how Saturn got its rings? This is believed to be why. A small moonlet happened to orbit too close to Saturn and was pulled apart by gravity, with the pieces now orbiting the planet as rings. And
Is that really? Man, I'm learning a lot today so far. I'm learning a lot today. Wow.
this, loyal theorists, defines the Roche limit, the distance away from a planet an orbiting body needs to be to not be torn apart by the planet's gravity. The Earth's Roche limit is 18,470 kilometers, or about 11,470 miles. That's about 1/20th the distance that the moon orbits at now. So if it ever ventured within that 18,000 kilometer limit, it would be pulled apart and the Earth would suddenly have itself some rings. And that, ladies and gentlemen, is how humanity could finally achieve its final form by blinging out our own planet.
What determines, forgive me if I'm having trouble thinking. I don't feel so well at the moment. But what determines, the size of something that will get destroyed in this situation? I'm pretty sure that made no sense. But like, you know, we have satellites around Earth all the time. Why aren't they getting ripped apart? Right? So obviously they're not big enough. What's the size limit that if it is revolving around Earth that it will get ripped apart? What's the size limit? Because we also have a freaking space station up there and it's not getting ripped apart because so obviously it isn't big enough. What is the size limit where it will get ripped apart? I think that made sense.
We liked it, and so we decided to put some lunar rings on it. Which brings us back to Odyssey. You ever stop to wonder why we're collecting moons instead of stars in this game? Could it be that what we're seeing here is early signs that Mario's moon is being ripped apart because it's orbiting within the mushroom planet's Roche limit? You probably haven't stopped and wondered that, and for as absurd as it might sound, it absolutely seems to be the case here. Notice those huge chunks of space rock scattered across the mushroom planet? We know for a fact that those are coming from the moon. moon, not only via their name, but also from seeing them on the moon itself. But to truly know for sure, we need to determine the Roche limit of Mario's Earth in the game, and then see where the moon falls relative to it. Now,
Okay, so I think I've got it. So what he's getting at is that the moon is in the Roche limit, so parts of it is getting ripped off and falling to Earth. So the whole lunar apocalypse thing here is that the moon has potential, or might have potential, to, you know, collide with the Earth or something like that. I think I've got it.
as you can imagine, that involves a lot of math, so I'll try to cut out anything that isn't too interesting. Scientists are Little Mooners, sponsor of the day, but hey, that's...
Was that a YouTube poop? What? Oh, okay, so he cut out the, okay, I get it.
Just a theory. Sorry, maybe I cut out a bit too much there. In all seriousness, though, the Roche limit of the planet is equal to 2.4 times radius of the larger object times the cube root of the density of the larger object divided by the density of the smaller object. And
dude, I barely got through math in school. What the? How am I supposed to do this? How am I supposed to figure this out?
as you can probably tell, there is a lot of stuff in that equation that we don't know. I mean, I just admitted 2 paragraphs ago to not being able to find the size of the planet. So without that, how do we have even a ghost of a chance of figuring out the radius of the planet, let alone the density of the planet? And then we gotta do the same thing with the moon. Well, as it turns out, we don't actually need the exact distances as long as a common unit is used throughout all of these calculations. So stick with me here and let's just base everything off the moon's radius. Give it a variable, let's call it little r. Now, as you zoom out to the overworld map, there are 2 frames where Mario's moon and the planet are side by side. And that's important so perspective doesn't distort their...
Is that side? That doesn't look side by side. Is it? It looks like the Earth is closer and the moon is further away. If that's the case and you're basing everything off of this, everything's wrong.
Their ratios. Taking pixel measurements from both of these frames, we can see that the moon's radius is about 30% of the radius of the planet. Now, earlier when I issued you the Mario Odyssey challenge, I said that the ratios on the screen might not be 100% true, but luckily we can also double check this. In New Donk City, there's a model of the Earth and the moon on the ground in front of City Hall. And wouldn't you know it, but once again, the math checks out. In this model, the radius of the Earth is determined to be 3.3 moon radii. And with that, we can say that the moon radius equals little r, and Mario's planet radius equals 3.3 times little r. Since we're eventually working our way to finding density, the next step is to find the mass of both Mario's Earth and Mario's moon, which again seems...
Matt, I think you should be a teacher. I think you'd be a great teacher. Especially if you could bring these kinds of, like, theories and that to class. I think a lot of kids would like that more than their normal math class. Like, when I was in school... Oh, goodness. I was not the best student. Especially at math. I was bad at math. Oh, what a nightmare.
Seems like it should be impossible, but luckily we have another secret back door here. Gravity. You see, when it comes to finding the properties of planets and stars, there are a lot of different formulas that we can use, since, you know, there's no actual way for scientists to weigh a planet without using some form of math. So here we can use gravity to calculate the mass by using the following equation. Mass equals acceleration times radius squared over the gravitational constant. That acceleration right there, it's as easy as finding out how fast Mario falls after jumping. First, on the mushroom planet.
Okay, I get it. My goodness, this freaking, it's too early in the day to be trying to wrap my head around this kind of stuff. I'm getting it so far, but I was not expecting this.
And then again on the moon. Something we've done a bunch of times here on the channel, especially back in my episode covering Mario's performance at the Olympics, where we found that the Mushroom Kingdom's gravity is more extreme than Jupiter's. Anyway, for that, all we need is the distance that Mario is falling and the time it takes him to fall. Plug those numbers into this equation and we get, holy jeez! On his home planet, Mario's normal jump has a downward acceleration of 70.16 meters per second squared. That is well over 7 times Earth's normal gravity. Seven times? That means that the planet is over 7 times the size of ours, doesn't it? Is 3 times Jupiter's gravity, and it's over double what it's been in any other 3D Mario game. If you're wondering why Mario feels heavier and falls faster in this game, well then, there you go. It's not Mario packing in the cannoli, it's his planet putting on the poundage. We do the same thing on the moon, and we get an acceleration of 11.74 meters per second squared. 1.19 g-forces, which is pretty incredible when you think about it. This right here, this is how much Mario would be able to jump if he were subjected to our measly gravity. Now with those accelerations in hand, we go all the way back to mass for both the planet and the moon. Since this is just some basic calculations, let me just burn through this quickly by speeding things up. Dumping the acceleration numbers, making sure to leave 3.3 r for radius of the planet when calculating for Mario's Earth, and just regular old little r when calculating for the moon, and we get ourselves a mass of 1.14 times 10 to the 13th r squared kilograms for the planet, 1.75 times 10 to the 11th r squared kilograms for the moon. Now with the mass and radius of each body determining the density, the final part of the Roche limit equation is a snap. Density, remember, is just a trip to the DMV. D equals m over v, mass of the object divided by the volume of the object. Volume of the sphere, which applies to both the moon and the Earth, is calculated at 4/3 pi radius cubed.
What did MatPat do before YouTube? Was he actually a teacher? That's like the only thing that makes sense. Either that or he was like, I don't even know, like, where would you even, like, start to learn all of this kind of stuff? Because in high school, they don't teach you this. So MatPat was obviously either in university for math, or he was a teacher, or, I don't know, like how do you just pick this stuff up? Like, that's crazy.
Boring with math, it's basically 150.53 r cubed for the Earth and 4.19 radius cubed for the moon, which leads to densities of 7.6 times 10 to the 10th divided by the radius of the moon for the Earth, and 4.1 times 10 to the 10th divided by the radius of the moon for the moon. And that finally means that we have all the variables that we need for the Roche limit equation. As a reminder, the Roche limit of a planet is equal to 2.4 times the radius of the larger object times the cube root of the density of the larger object divided by the density of the smaller object.
Oh my goodness.
The planet is 2.4 times the radius of the larger planet, which is 3.3 r, since remember, it's 3.3 times the radius of the moon times the cube root of that mess of densities that we just calculated. Don't forget that when you divide a complex fraction, you multiply by the inverse, so those little r's cancel out over there as well as those 10 to the 10ths. You got all that? No? Perfect. Don't worry, you didn't miss a thing. Running through...
Good. Because if I had to understand it, oh, we'd be here all day. We'd be here all day.
All of those numbers, we see that the Roche limit is equal to 9.66 moon radii. In other words, thanks to all the math that we just ran through, we proved that if Mario's moon is within 9.6 moon radii from the center of his Earth, it will be slowly getting torn apart by Earth's gravity, which would give us the reason why we have hundreds of mini-moons and moon rocks all scattered across the surface of Mario's planet. And
Alright, so I think I'm caught up now to what's going on and everything like that. So now the question is the moon close enough to start getting ripped apart as it seems it is?
You know what? That's exactly what's happening here. You know how in the moon there's a spot where you can see the Earth not so far off in the distance? Well, using that vantage point, it seems pretty obvious that the moon is super close to Mario's planet. So
it does, because I think in actual, like, space photos, isn't, like, the Earth, like, really small?
Could just assume it's within that Roche limit, but that's not good enough for me or the standards that I have for this show. So using that vantage point coupled with the in-game compass, you heard that right, using the in-game compass to measure actual angles, it may seem unbelievable, but it's actually possible to determine the exact distance with trigonometry, chord lengths, and good old SOHCAHTOA. But since this is the sort of math that I personally never wanted to show up in my life again, and I can only
SOHCAHTOA? I thought that was the stuff that the natives, like, smoked out in the desert.
assume like 3 of you actually can.
That can't be it. No, what's it? Peyote. I don't know, man. It's too early in the day.
Care about this type of nitty-gritty detail? I'll do it as a mini-theory if enough of you in the comments are actually excited about that sort of thing. Suffice it to say, running all of those numbers, you get the moon sitting just about 5.5 moon radii away from the Earth, confirming that it's within the Roche limit and that it is getting eaten alive by the planet's gravity. And remember, this isn't hypothetical. This actually isn't just a theory. This is truly how Mario's planet would be behaving relative to Mario's moon. It would be eating it alive.
So yeah, it does seem like it is eating it alive. And that would explain why they're finding moon pieces and there's moon rock everywhere. That makes, 100% makes sense. But I don't understand why it's taking it so slow. Like, wouldn't it, you'd think it would happen faster, right? Than what seems to be going on.
That is insane! And while that goes a long way to explain why moon rocks and multi-moons are scattered everywhere, it also spells out some dire consequences headed straight to Mario's planet. To give you an example, consider this. When our sun starts to burn out and turn into a red giant, it's predicted that our moon will be pulled out of orbit and it'll be pulled closer to Earth, crossing the Roche limit. At that point, it'll be torn apart. On the plus side, it'll give our planet a cool temporary ring. On the downside, it'll shower the planet with huge pieces of moon debris, destroying all sorts of land, throwing tides into chaos, and sending the planet into another wave of extinction as space rocks crash into the surface around the world.
Oh boy, I can't wait.
Cause yeah, while some of those chunks will orbit as pretty little rings, most of it'll just get pulled down by gravity onto the Earth's surface. And that is the fate that Mario Odyssey has already started to allude to for the Mushroom Kingdom. And that is the fate that is determined for it based on the science. And it certainly doesn't help that in the final battle, Mario speeds this process along by destroying huge chunks of the moon's core. So enjoy running around to collect those moon rocks while you can, Mario. Pretty soon you won't have a choice as they hurtle themselves towards you.
Why did you draw nipples on him? What the? Or are those buttons, like on his, whatever the friggin' thing's called? Like, it looks like nipples, but I think it's probably buttons. My goodness, that was insane. That's probably, like, the most complex game theory that I've had to get my head around. But, I mean, if you break it down into simpleton terms, it makes sense. It really makes sense. But anyway, I hope you guys liked this video. If you did, make sure you give it a thumbs up, possibly share with a friend if you do, and subscribe to the family. Also, make sure you go subscribe to the Game Theorist. And with that being said, I'll see you guys next time. Boop!